I greet you all. How are you? So in this tutorial we are going to talk about truth tables and logic gates. We are not going to take too much on the truth tables because in class we talked about truth tables. Then my interest is on logic gates today. Alright, so a truth table is just something containing all possible inputs and output combinations of a function. If a function like y is maybe equal to b and then b plus, let's say c, a truth table for this function is a table for which all possible outcomes of y are given. So you first look at if b is true and c is not true, and then if b is false and then c is true. There are so many outcomes, so we looked at these truth tables, and then a truth table has these values like you see here. There is a t for a true and then an f. Sometimes we use 1 to mean a true, and then we use a 0 to mean a false. So, and then that's it. In circuits, automatically a 1 represents on, and then a 0 will represent off. That's in circuits. Alright. In logic gates, of course, these are the basic combinations or basic operations that we have: the AND, the OR, and the NOT, because other operations can be derived from these. Alright, so this is a sample of the truth tables, and this is the AND. If they say maybe a function y is equal to a is equal to x. Okay, let me use what they have used. Let's say we have a function y. We have these variables as y, we have the x, and then we have the z. So if we have a question and it's telling us to find z, which is equal to maybe x and then times y, this is the AND in most cases. Okay, so this is the AND, and this is how it is supposed to be. So you have all possible values of x, which is here, and then all possible values of y, which is there, and then you derive x from those. All right, you derive z rather. So we write as usual all possible values. This is 0 0, or maybe this x is true and whatever. So you write 0 1 0 1, and then you write 2 0 0 and then 1 1, just using the other logic from the class. Alright, so the AND means both have to be true. Okay, both have to be true. The y and the z have to be true in order this AND to be true. So if we have x 0 and y 0, automatically we have a 0. If I give you an example of sometimes if you want to call some two people and then you say I want to call Esther and maybe Sam. If Esther comes and then Sam doesn't come, it's not a true. If Sam comes and Esther doesn't come, again the AND is 0 because they are both not there. And then if Sam comes, still Esther doesn't come, the AND is not true. But if both come, then we have a 1 here. All right, then the O is a plus. So if we have Z is equal to an X maybe plus Y, we get all possible values of X and all possible values of Y, so they are here. So if you call Esther and Sam and the two of them do not come, that means the O is 0. O is true if one of them comes, if at least one of them comes, and if they come both of them, then it's okay, still you have them, still you have at least one. Alright, so I won't take too much. Then the not get or the not operation is just an inversion. It tells me that give me a boy and I give you a girl, or maybe give me love and I will give you hatred. Alright, so maybe, so it's an opposite. Give me a 0 and I'll give you a 1, and then give me a 1 and I'll give you a 0, such things. Alright, so logic gates, and this is where we are going to have a little bit too much interaction on logic gates. In physical devices, the logic gates are there. Actually, logical gates are the physical devices that do perform operations. These operations can be done on a number of inputs and then give at least one output or more. So they perform logic operations on one or more logical inputs, and then they bring out some outputs. Produces a single logic output. This is, for example, the logical sum, then the logical multiplication, and then the logical inversion. The logical sum is the addition, or we are saying this is the OR operation. And then the logical multiplication, this is a times, and this one we shall call it AND. Okay, so this is the AND operation. And then the inversion, this is going to be the NOT. Okay, it's going to be the NOT. So all these ones have their symbols of how to represent them. For example, the OR gate is going to have its own symbol, the AND gate, and then the NOT gate. If you're given a function like f is equal to maybe x, then plus z, then it means here you have what we call the OR gate. All right, it means you have the OR gate because the OR gate has a plus. Guys, don't ask me about the minus, because the minus is the same as the OR gate, which is a plus. If I have 2 minus maybe 3, you may believe that I have 2 plus maybe negative 3. Okay, I have that. So if I have this, that means that this whole thing still comes back to an OR gate. All right. So don't ask about the negative. So we are going to consider a plus because we know that here we can as well cater for the minus somewhere. All right, so this is the historical background of these gates. In the first computers, switches were opened and closed by magnetic fields produced by energizing coils in relays. So at first we used to have computers that are bigger than the room where you are seated, or maybe if you're watching this tutorial from outside, we had things, and there are very many. So, and then magnetic fields were the ones that used to open those gates and close them. So when we came in the early 90s, there we got some switches that can turn on and off some kind path, and then afterwards vacuum tubes came in, and today we have transistors. Those transistors are the ones that have some logic gates inside them that really do a work. So you can just at your own time read through this content, and then you can be able to analyze it. Alright, so these are the categories of logic gates. We have the basic gates. The basic gates are basically the NOT, the OR, and then the AND. We have talked about this. So the NOT gate is the negative, or you can call it the inversion. We say it is an opposite. You give me this, I give you the other. So the OR gate is going to be the plus, and then the AND gate is the multiplication. Universal gates, this is the NAND, and then the NOR gate. Then they are antimatic, they called antimatic, arithmetic, or something. I think there is some small error here, if I'm not mistaken. Okay, so the exclusive OR and then the exclusive NOT is also there. So these are the symbols that we are going to use, and the AND gate is going to be represented by this. And if you have X and Y and you pass through the AND, you get a function F. This is equivalent to F, okay, F equaling to X times Y. Okay, so this is the same thing, and then the OR gate is equivalent to X and then plus Y. Okay, plus Y. Then this is an inversion. An inversion takes in one value, and these are two values. So this one gets an opposite of X. So if I have an X here, when I reach here I have a Y. So this dot here can be written anywhere. You can write it here at the beginning, or you can write just here where it is. So don't worry, people. This is the buffer. The buffer has no this, and the buffer has no any change. If you pass an X in the buffer, you still have an X as a result. It doesn't cause any change. And then the NAND gate actually negates the AND. Okay, so it negates the AND. If you have X and Y, pass through this together. So these are others, the null, exclusive, OR, and others. So you read through these guys, and then you can be able to catch up. Alright, so let's look at the waveform or the behavior of these things. If I have X and I have Y, if I write all possible outcomes of X and Y, so one time I may have X on, X off and Y off. So when X is off, then my bar comes down. So if I have a 0, and then a 1, and then a 1, so this means that of course 0 goes up, 0 goes down, and then a 1 goes up. Okay, so I come when I'm at up, and then when I reach here, this is a 0, I go down. Still this is 0, I continue down, 0, 0, I continue down, and then I'm meeting a 1, I go up, and then I complete because that's the 1, and then you go. So this is the possible outcomes of this. So if you have also, we are relating, this is x and this is y, so we are relating. So if x is not on and then y is not on, if x is on and this is on, this is 0 and then this is 1. So as we said, I come up, when I meet a 0 I go down, continue, when I meet a 1 I go up, when I meet a 0 I go down, then when I meet a 1 I go up, like that, and then I complete like that. So this is the wave formula which is here. Alright, so now we want to compare basing on these values. We now go to this, we go to the AND. So let's compare line by line. If x is 0 and y is 0, we said the AND is what? Is 0. Okay. If x is 0 and then y is 1, the AND still remains 0. We said the AND is true if we have one, if all of them are true. Okay, so if we have x as 1 and then y as 0, still the AND is 0. Then if we have this one and this is 1, still this is 1. It becomes a true. So if you want to draw it, this is a 0, this is a 0, this is a 0, and then this is a 1. So we said when you come from up and then you reach 0s, you go down up to when you meet a 1 and then you continue. So this is how it comes up like that. So if we have the O, x or y, this is a plus, okay, it's a plus. So come up with this and then come up with this. This is a negation, the note of x. So if these are zeros, here I write ones, and then if these are ones, here I write zeros, and so on and so forth. So alright, so that is it. Now let's go to diagrams. I hope we shall start from here in the next tutorial. Please endeavor to watch the next one because it's the original. That's actually the fact why we need to learn the logic gates. We have just been looking through some simple revision of the logic gates and then the truth tables. So let's start from here.